Have you ever looked up at the sky? You see a tiny silver speck. It moves silently, effortlessly, across the vast blue canvas. This speck is an airplane. It travels at incredible speeds, sometimes close to 900 kilometers per hour. How does such a heavy machine achieve this? How does it conquer gravity and distance with such apparent ease? The answer lies not in magic, but in science. It lies in human ingenuity, our relentless quest to understand the world. The key to this modern marvel of flight is a powerful, intricate device. This device is known as the jet engine. It is the muscle and the heart of these magnificent flying machines. Think about the sheer scale of our planet. Vast oceans, towering mountain ranges, sprawling continents. For much of human history, these were formidable barriers. Journeys that took months, even years, by land or sea can now be completed in mere hours. This revolution in travel, this shrinking of our world, is largely thanks to the jet engine. It has connected cultures, fueled economies, and expanded our understanding of the Earth as a single, interconnected sphere. The story of the jet engine is a story of human curiosity and triumph. At its core, a jet engine is a type of engine that produces thrust. Thrust is the pushing force that moves an airplane forward. But how does it create this push? Imagine blowing up a balloon and then letting it go. The air rushes out one way and the balloon shoots off in the opposite direction. A jet engine works on a similar idea, but on a much grander, more controlled, and vastly more powerful scale. A jet engine is essentially an air-breathing machine. It takes in a huge amount of air from the front. It squeezes the air, adds fuel to it, and then burns the mixture. This creates a powerful blast of hot gas. This gas then rushes out of the back of the engine at very high speed. This rapid expulsion of gas is what propels the airplane forward. It's a continuous process, a constant flow of air in and hot gas out, generating relentless power. Think of a jet engine as a carefully orchestrated dance of air and fire. The journey of air through a jet engine begins at the very front. Here you will often see a large, impressive set of blades. This is the fan. On many modern commercial airliners, this fan is huge. It can be several meters in diameter, a spinning marvel of engineering. Its primary job is to suck in enormous quantities of air. Think of it as the engine's giant mouth, taking a massive gulp of the atmosphere with every rotation. These fan blades are not simple pieces of metal. They are incredibly sophisticated. They are shaped like airfoils, similar to the wings of an airplane. This special shape allows them to grab the air efficiently and accelerate it. Some of this air goes directly into the core of the engine. But a large portion of the air, especially in modern turbofan engines, actually bypasses the core. This bypass air is still accelerated by the fan and produces a significant amount of thrust. It also helps to make the engine quieter and more fuel efficient. Once the air passes through the fan, a portion of it enters the engine's core. The first part it encounters here is the compressor. The compressor's job is, as its name suggests, to compress the air. It squeezes the air into a much smaller space. The compressor in a jet engine does this on a massive scale and at incredible speed. This compression is vital for making the engine powerful and efficient. It prepares the air for the next stage. The compressor is made up of many rows of small airfoil-shaped blades. There are rotating blades called rotors and stationary blades called stators. The rotors spin rapidly, pushing the air backward and increasing its speed. The stators then direct this airflow and slow it down slightly, which further increases its pressure. This process is repeated through multiple stages. Each stage adds more pressure, squeezing the air tighter and tighter. By the time the air leaves the compressor, its pressure might be 30 or 40 times greater than when it entered. This highly compressed air is now packed with potential energy. After being intensely squeezed by the compressor, the high-pressure hot air moves into the combustion chamber. This is where the real fireworks happen. It's the fiery heart of the jet engine. Inside the combustion chamber, a fine mist of jet fuel is continuously sprayed into the compressed air. This fuel is similar to kerosene. Once the fuel mixes with the hot compressed air, it ignites. This isn't a single explosion like in a car engine cylinder. Instead, it's a continuous, controlled burn, a sustained inferno. The temperatures inside the combustion chamber are extreme. They can reach over 2,000 degrees Celsius or 3,600 degrees Fahrenheit. This intense heat causes the gases inside the chamber to expand dramatically. The air and burnt fuel transform into a torrent of superheated, high-energy gas. This rapid expansion of gases is the key to the engine's power. The combustion chamber takes the potential energy stored in the compressed air and the chemical energy in the fuel. The incredibly hot, high-pressure gases now blast out of the combustion chamber. Their next destination is the turbine. The turbine looks a bit like a windmill or a series of pinwheels placed directly in the path of this fiery exhaust. It consists of several stages of blades, much like the compressor, but instead of using power to compress air, the turbine extracts power from the hot, expanding gases. As these gases rush past the turbine blades, they make them spin at very high speeds. This spinning motion is absolutely vital. The turbine is connected to the compressor and the fan by a central shaft, or sometimes multiple concentric shafts. So, as the turbine spins, it drives the compressor. This allows the compressor to keep squeezing fresh air coming into the engine. It also drives the fan at the very front, which pulls in the initial massive gulp of air. The turbine, therefore, is the powerhouse that keeps the entire engine running. The turbine's job is to extract just enough energy from the hot gases to power the compressor and the fan. The remaining energy in the gases is what will be used to produce thrust. After passing through the turbine, the hot gases still possess a tremendous amount of energy. They are still moving very fast and are very hot. The final component they encounter before exiting the engine is the nozzle. The nozzle is essentially a specially shaped duct at the very back of the engine. Its primary purpose is to accelerate these exhaust gases even further. It squeezes the flow of hot gas, forcing it to speed up as it exits. Think of how water speeds up when you put your thumb over the end of a garden hose. This acceleration is key to generating thrust. The faster the gases are expelled from the back of the engine, the greater the pushing force, or thrust, on the airplane. The shape of the nozzle is carefully designed to optimize this acceleration. The roar of a jet engine, that iconic sound of modern air travel, largely comes from these high-velocity gases exiting the nozzle. The mixing of these fast-moving hot gases with the cooler, slower-moving air outside the engine creates intense turbulence. This turbulence generates powerful sound waves. So, the nozzle is the grand finale of the air's journey through the jet engine. So, we've seen the air go in, get squeezed, burned, and blasted out the back. But how does this backward blast of hot gas actually push a giant airplane forward? The answer lies in one of the most fundamental laws of physics. It was described by Sir Isaac Newton over 300 years ago. It's his third law of motion. You've probably heard it before. For every action, there is an equal and opposite reaction. This simple statement is the key to understanding jet propulsion. The jet engine exerts a powerful force on the gases, throwing them backward at high speed. This is the action. According to Newton's third law, the gases must exert an equal and opposite force on the engine. This reaction force pushes the engine and therefore the airplane attached to it forward. The engine throws mass, air and burnt fuel, backward, and the universe pushes the engine forward. The amount of thrust a jet engine produces depends on two main things. First, how much mass, air and fuel, is being expelled per second. Second, how much the speed of that mass is increased by the engine. Not all jet engines are created equal. While they all operate on the same basic principles we've discussed, there are different types designed for different purposes. The earliest type was the turbojet. In a turbojet, all the air that enters the engine goes through the core, the compressor, combustion chamber, and turbine. These engines are very powerful for their size and can produce very high exhaust speeds. This makes them suitable for very fast aircraft, like supersonic fighters. However, they can be quite noisy and less fuel efficient at lower speeds. Then came the turbofan engine, which is the most common type found on commercial airliners today. Remember that big fan at the front? In a turbofan, a significant portion of the air moved by the fan bypasses the engine core. This bypass air creates thrust, just like the hot jet from the core, but it's cooler and slower. This makes turbofans much quieter and more fuel efficient than turbojets, especially at the speeds passenger planes fly. Another type you might encounter is the turboprop. In a turboprop engine, the turbine drives not only the compressor but also a propeller at the front. The propeller moves a very large volume of air, but not as fast as a pure jet. Turboprops are very efficient at lower speeds and altitudes, making them ideal for smaller commuter aircraft and cargo planes that operate from shorter runways.